This is part 2 of section 1.4 dealing with continuity. In this video I'm going to go through 2 more examples of how to use the definition of continuity to determine if a function is continuous at a particular point. This example has a piecewise function. It's defined anything that is less than or equal to -2, we're using the top definition. Anything between -2 and 3, we're going to use the middle part, and all values of x that are greater than or equal to 3, we're going to use the bottom. So to determine if it's continuous at -2, relying upon the definition, I need to first of all check 3 different things. First of all, is it going to be defined at the point? So is it defined at -2? Is the function defined? Does the limit exist at -2? And then, does the limit equal the definition? So once I check these 2, this last one is saying, are these 2 going to be the same? Well, first of all, is it going to be defined at -2? This says x is less than or equal to -2, so it is going to, in fact, be defined, because I can plug in -2 into this definition, into this piece, because I would get -2 to the second power plus 3, which would give me 7. So the definition of h at -2 is going to give me 7. Next thing I have to check to see if the limit exists. Because it's a piecewise function, I have to figure out if both sides have the same limit. So the limit approaching -2 from the left. Well, -2 from the left is again going to be using the top portion, so it's going to be -2 squared plus 3, which is going to give me 7. Now the limit from the right, all the values a little bit past -2 from the right, we're going to be using the middle definition. -4 times -2 minus 1. These 2 negatives give me a positive 8 minus 1, and it gives me a 7. So the limit, in fact, does exist. They both meet up at 7, so this limit does exist, and it equals 7. So I could even say that the limit as x approaches -2 of h is equal to 7. And then the third thing is that the limit equals the definition, which is in fact true. So the third thing is that h of -2 equals the limit at x is -2. And for these piecewise functions, you often get the third one just by doing the first 2, because you're going to have to plug it in, be able to plug it in somewhere, be able to have it defined somewhere, and the limit hopefully will exist. And if it does, then usually these 2 are going to be the same. So oftentimes for these piecewise functions, they'll get kind of the third one just by doing the first 2. Alright, now we're going to investigate what the function, if the function is continuous at 3. Now I'm going to go figure out if it's continuous at x equal to 3. So first thing I have to again do is figure out if it's going to be defined at 3. Well, if I plug in 3, I have to use the bottom definition, because that's the way the piecewise is defined. So I can plug in 3 and get 3 squared plus 1 all over 3, which gives me a 9 plus 1, which is a 10 all over 3. So it's defined? Yes. 2, I got to figure out if the limit exists as x approaches 3. Alright, so the limit from the left is going to be the value is a little bit past, or a little bit before 3 on the left. That's going to be this definition. So all the things to the left of 3 are this definition, so it's going to be -4 times 3 minus 1, which is going to give me -12 minus 1, which is negative 13. And the limit from the right, all the values that are a little bit past 3 from the right, that's going to be this definition, the bottom one. It's going to be 3 squared plus 1 all over 3, which is going to give me 10 over 3. You can see that this limit is not going to exist because different sides gave me different values, so this limit does not exist. And since the limit does not exist, you can say that the function is not continuous. At x is equal to 3. And furthermore, because we have a jump, the limit does not exist from both sides. The jump creates a non-removable discontinuity, a non-removable discontinuity. So, limit not existing creates a jump in the graph, which is a not continuous and also non-removable. Alright, last example is pretty typical on the multiple choice AP exam, which is finding a value of k to make a function continuous. So they have some constant. In this example I chose k, and we want to make it continuous at the point that's being split. So because it's defined to be x is greater than or equal to 3, I know it's going to first of all pass the first part of the checklist, which is it's being defined. So really I have to just focus on whether the limit exists at the point or not. So I need to make this limit exist for it to be continuous. So really I need to figure out what value makes this limit exist at 3. Well, the limit existing at 3, because it's piecewise, means that the limit of 3 from the left has to equal the limit of 3 from the right. So if I plug in 3 from the left, it's going to be the top one. Now k is the unknown, so I don't know what k is. I'm just going to leave it as k. So k times 3 minus 2, I'm just going to write it as 3k minus 2. Plugging in 3 for the right down into here, it's going to be 5 times 3 plus 1. So this gives me, let's see, 15 plus 1 is 16. So now 3k minus 2. So now this just turns into an algebra 1 problem because k is what I have to solve for. So I move the 2 over, it's going to be 3k equal to 18. I can divide both sides by 3, so k is going to equal 6. So in order for this to be continuous, the constant k has to be equal 6. And that's it.